I'm Zane Landers. I guess we're recording this now, so I'll just keep it quick since I already introduced myself to everybody live. I'm from Tucson, Arizona, though I'm originally from Stamford, Connecticut, and I have quite a lot of experience of observing the night sky, both under the fantastically dark skies we have here and the more light polluted places in the East Coast. I've owned over 450 telescopes. I fixed them for fun, and for a long time I was buying and reselling them, which is how I got to that gigantic number. And I've also ground my own mirrors for telescopes from scratch. Currently, actually helped my roommate grind this one. This is a 16-inch. I'll talk about it in a bit. Not that fragile. See? Um, I've been a strong proponent of building telescopes, usually simply because it's cool. But recent factors have made it something that I really think is worth advocating for, not just for the mere concept of, oh, it's cool and you should, but there are a lot of practical considerations that make it really worth considering doing, and it's a really fun project. And even if you're not interested in building your own telescope, learning about how it works is something that is invaluable and it's great to be able to explain and understand stuff as well as be able to fix your own equipment even if you didn't build it. Arrow keys don't. Okay, I have to click. Fascinating. So obviously, if you've seen a telescope, you're probably, or think of a telescope in your head, you're probably thinking of like a refractor, like the one on the left, which is this shiny, long tube thing with a lens at the front, or maybe a thing that still has a lens at the front, but is shorter and more compact, but something on a tripod, like the Schmidt-Cassegrain on the right, which is my Celestron C11. Now, these telescopes look really pretty, and they do have things like motorized tracking, and of course, there are some very important use cases for stuff like epichromatic refractors and Schmidt-Cassegrains for things like astrophotography. When it comes to just looking at the night sky, for starters, these things are plain unaffordable, they're impractical, and you simply can't get a very large one, a large refracting telescope of even 6 inches in diameter. So, a lens about this big is something that you can barely set up yourself and costs thousands of dollars for a good one. The 11-inch Schmidt-Cassegrain I own would be thousands of dollars new and is barely manageable by one person. And again, bottom line, they're also more complicated and just not the best way to get out under the night sky if you're just getting started or want to do it on a budget. Dobsonian telescopes are really ugly, and I've heard a lot of people argue otherwise, but I'm going to be honest, I love these things, and they look terrible. Just to give you an idea, these are also some Dobsonians here. I'll talk about them some more in a bit. But the one on the left in this slide, there's two. There's a commercial 25-incher, that's a 24 built. And on the right is a more classical Dobsonian built by John Dobson. And you might see that that thing is just a giant tube that's about 10, 11 feet tall and looks like a big cannon. The ones on the left kind of look like that, but in actuality, it's a thin metal skeleton that breaks down and then you put a piece of fabric over it. Now, the thing is that if you think about aiming one of these around the sky, the simple cannon-like motion of swiveling it left and right and then pushing up, down is a lot more intuitive than having to unlock a bunch of clutches or deal with gears, cables, knobs, or any electronics. You just push it, you let go, it stays where you want to point it. Now, John Dobson, the guy under the golden tube there on the right, you can't really see him that well, he built this telescope behind me, and as well as that one, and he invented these types of telescopes. Now, Dobson came up with a lot of really important ideas that define these telescopes, but the most important is the friction movement I mentioned. There's no clutches or clamps or anything or gears. With a Dobsonian, the telescope pivots left to right and up and down on basically various types of plastic. The secret is friction. You see, this is spinning on a vinyl record against 3 small Teflon pads. I'm standing on the Zoom thing here. I don't know if you made me bigger or not. I hope probably should have asked that. But they are very easy to aim around the sky and use, and there's not a lot of real technical knowledge required to set one up. If you just want to look at the moon and planets, all you just have to do is plop your telescope outside, look through the finder, and then it's there in the eyepiece. There's no tripods to even worry about because these things sit on the ground. They're also really affordable. An 8-inch Dobsonian, like the one behind me new, is about $600 to $800 to buy, but you can build one for about half that. The other telescope behind me is a 3D printable telescope called Hadley, and Hadley's really cool, and I'll get to that in a minute. So I haven't really explained what a Dobsonian telescope is other than that whole cannon thing, but the basis is that a Dobsonian is a type of telescope called a Newtonian reflector that has a primary mirror that's shaped like a parabola, and it's sort of like a salad bowl shape, and it collects light and focuses it onto a flat mirror that bounces the light off to the side into an eyepiece. Because, if you just stood at the focus of the primary mirror, your head would block everything unless you had a very, very, very big mirror. So that's why the secondary mirror is there. Now, when we're building telescopes, we usually just buy those secondary mirrors because they're not terribly expensive until you get to very large sizes, and making one yourself is an utter nightmare. I've looked into it. It is just not worth doing. Now, there are a lot of different ways you could accomplish this basic design principle of tube that pivots up, down, swivels left, right, and has the mirrors in it. And that varies from collapsible skeleton truss tube, like my 20-inch there that you can see the frame of with my cat standing in the middle, to the 3D printed strut tube design of telescopes like the Hadley behind me or the 3D printed one here on the right. But regardless of how you exactly choose to put the optics in a housing and customize the exact parameters, the basis is the same. It swivels upright. It swivels up, down, left, right on friction-based bearings, and it's got a parabolic primary mirror. And you can make that primary mirror yourself at home. Again, my buddy is working on one of these. This is a 16-inch diameter mirror I'm holding here. I hope you guys can see me. And it's actually an old porthole. These are actually really great materials for making mirrors because it's quite hard to find precision annealed glass nowadays for a reasonable price, but you can still find shipped portholes, and they are pretty easy to test for whether or not they're tempered. If they're tempered, they'll explode when you try to grind them into a mirror. Now, Dobsonian telescopes tend to be made out of wood because wood is easy to work with, and anybody with a circular saw and a drill can make a basic box and some other things out of wood, which is really all you need to do with one of these. But lately, there's been more emphasis on 3D printing, and it's gotten easier to make things yourself out of metal. And of course, nowadays, there are entire services on the internet that can CNC things out of metal or plywood for you if you don't have any tools yourself. Here's a diagram of the light path in a Newtonian reflector or Dobsonian. So you can see the primary mirror the focal point of it is a little past where the secondary is, and then the remaining travel is between the secondary and focuser, and then it forms an image in the focuser, and you put your eyepiece there. An eyepiece here behind me. Of course, these are interchangeable with any telescope. Exactly how you choose to provide a focusing mechanism is also something that can get quite interesting. That varies from the precise machined metal Crayford focuser in this diagram here to, well, this telescope behind me came with a piece of cardboard inside another piece of cardboard, and the smaller one was the diameter of an eyepiece, and you slid that back and forth to focus. Dobson thought that worked fine. It is terrible. And also, if you try to use it with other people and they push their head into it, it'll just push it in. So that's quite annoying. But again, whatever works, works. If you just want your telescope to function, the simpler, the better. And that's what John Dobson's philosophy of this was all about. Now, you might be wondering, okay, so that's great. I've explained why Dobsonians are cool telescopes. So why would I build one? That seems like a lot of effort. Making things is hard. What if I don't have tools? Well, for one thing, it's actually kind of hard to even get a new telescope right now. Pricing has gone insane. And when I got into astronomy, you could buy an 8-inch Dobsonian telescope for $300. Today, it's a good deal if you get one for 2 times that. And that also the quality of a lot of commercial scopes has gone a little downhill. And now, thanks to issues in China and the shipping attacks in the Red Sea, there are just stock issues at a level that wasn't even happening during COVID when people were ordering telescopes like crazy. And another thing to consider too is that nowadays, when you're building your own telescope, there's a lot more information online out there to build something that's really optimized and better than anything you can buy and really fits your exact needs. And even if you don't own a single tool and live somewhere where the idea of making any kind of loud noise with a drill is even out of the question, there are services, again, that can CNC cut or 3D print things and mail them to your door, and you can assemble them like Legos. Which leads me into the next thing, the Hadley 3D printable telescope, which I helped design with a friend of mine, Jonathan Kisner. He is very good at coming up with 3D printable stuff. The Hadley is impressive from a technical viewpoint, not just because it's a printable telescope, but also because it's pretty easy to 3D print, which a lot of 3D printed things require that you print supports and such. And I'm very bad with 3D printers, and I can still manage to crank out Hadley parts. So It can't be that hard. I have an Ender 5, but you can print these on pretty much anything. Now, Hadley is a 4.5-inch telescope, and it's a little unusual in that, to make a long story short, there's a particular standard spec for these mirrors, and you can yank them out of some pretty bad, otherwise bad telescopes, or just order them bulk, or find them on Amazon. And you can build the whole telescope for about half as much as it costs to buy a 4.5-inch Dobsonian new. This is really attractive because a telescope like Hadley or something similar in capabilities is really kind of the minimum that's really worth considering compared to a pair of binoculars for your first telescope. And now that the prices have really gone up, Hadley actually is cheaper, even if you do have to outsource the printing to somebody else, than it would be to buy a telescope new. And it really just kind of assembles like Legos. I have a Hadley behind me, and this one was one of the first ones that a friend of mine printed this. And this one's on a wooden base that I threw together, but you can 3D print them. And Hadley is just like the 8. It's super easy to just swivel around. It has this, I mentioned focusing devices can be a bit interesting. This one's just a giant screw. We call it a helical focuser. You just twist this big wheel. This was my contribution to the design. If you have a big wheel like this, you have an easier time making fine adjustments. And you just twist this inside this big plastic collet, and you can focus that way. And you look through the eyepiece here. And there's even a printable iron sight, so you don't have to buy anything to help you aim it. And this one uses wooden dowels for the tube struts, but you can use aluminum tubing, steel rods. Some people use electrical conduit. And it's also extremely lightweight. On even a pretty heavy wooden base like this, I can walk around with it one-handed, and that makes it really great for if you just want to go outside in a hurry and look at something. That being said, Hadley's not the only 3D printable telescope. People who have contributed to Hadley have gone off to design bigger versions, though a lot of them require rather hefty 3D printers or just aren't really cost effective. But 3D printing in general has allowed making precision parts for telescopes to become something that is no longer particularly tedious or time consuming. And even if you don't have a 3D printer and have no desire to use one, you can just find files for parts or, Hadley itself online and have somebody print it out for you. And again, it really assembles like Legos. Now, when Hadley was first out, there was not a 3D printable base, but some people have come up with various versions for one that look kind of like an erector set. It's pretty impressive. Obviously, of course, a lot of people want a bigger telescope, and that's where I'm more interested. Hadley's very fun, but it does assemble like Legos, and a small telescope is more for bright objects like the moon, planets, and double stars. If you want to look at galaxies or resolve stars in globular clusters, or have a chance at spotting Pluto, if you really care to, a larger telescope is the way to go. And of course, also, when you're looking at the moon and planets, a bigger telescope does gain you more resolving power, at least to a point. Now, of course, Hadley is kind of different from the conventional telescope making stuff in that, again, you just 3D printed and glue the mirrors in and then put the rest together like Legos. But it's not particularly hard to build a normal Dobsonian like this one behind me. John Dobson worked with pretty minimal stuff, and this 8-inch here, this is how it looked originally in the photo on the right, was built with nothing but a circular saw and a drill. The secondary mirror is held in place with roofing shingles, which not the way I'd do things, but it does work. The tube for this is made out of concrete form tube that you might see used to pour columns. You can buy them at Home Depot for $8. They're called Quick Read or Sonotube, but it's cardboard, but cardboard can be plenty strong, and once you reinforce it a little by adding hardware and so forth, it's more than acceptable. It's also really easy to work with. You just need to add the wooden, more printed or metal parts that hold your optics and focuser, and you're pretty much done. And all you need to really build other than that is a box to enclose the tube. Some kind of round things are needed for the altitude bearings. Now, if you don't have the ability to cut anything round, PVC pipe caps work. I did that for my first homemade telescope, and that'll perform the same function. And then you just need to cut some V-shaped notches for the altitude bearings, add some little feet onto the bottom board, and then you make a couple wooden boxes. It's one of the easiest woodworking projects there really is, and it's actually what got me into woodworking. Honestly, having made some nice end tables, those were more difficult than typical small Dobsonian like this. Now, at larger sizes, you do need to start considering things like a truss tube, and those can require some precision hardware to put together reliably the same way each time. And of course, supporting larger and thinner mirrors becomes a challenge. Now, there's a lot I can go into about that, and I've messed around with some very interesting stuff related to thin mirrors and so forth that's really cutting edge, but it would be rather complicated to explain, and you can always look that stuff up. The real appeal, again, of making your own telescope is not just in the fancy aspect of the tech and how precise it is, but it's also about, knowing how it works. You have to keep in mind that the mirrors inside these telescopes are precise to an accuracy of 1/1000th of the thickness of a saran wrap. The largest bump on these optics, if you were to scale them up to the size of the United States, would be about the size of a grain of sand, which might make you wonder how anybody can make the mirrors for one in their garage or their kitchen. And I'll get into that. Now, another thing to consider, of course, is the large telescopes are a bit of a commitment, and they do tend to get quite expensive, but the views to them are really unbelievable. The 24-inch in this photo allows you to see the pinks and purples in the Orion Nebula vividly, and the spiral structure in galaxies is obvious. This photo was taken at Lake Taconic State Park in upstate New York. And you can break one down, a telescope this size down to fit in a SUV or minivan pretty easily. And that's a 24-incher, which is about the biggest single-person telescope there is. And the thing is, at larger sizes, it isn't just a question anymore of, oh, it's cool, and, hey, I can get something maybe a little nicer looking and better design than anything I could buy. It really is just a cost issue. Due to the fact that there's just not a lot of demand, there's not a lot of people making large Dobsonian telescopes commercially, and the ones that are either premium or really not that well designed. And in any case, you're looking at something like $5,000 to $10,000 for a 16 to 20-inch telescope. Now, I'm about to start grad school. I don't have that kind of money, and most people don't, and most people can't throw that at telescopes. But if you're building your own telescope, you can build a 20-incher if you grind your own mirror or find a used one for only $1,000 to $2,000. If you want to make a 10-incher and grind your own mirror, you can make one for a couple $100, whereas buying a 10-inch is nearly $1,000 now. And of course, these larger telescopes are a bit more of a commitment and probably shouldn't be your first, but building one is undoubtedly the way to go on every level. Just there really isn't any reason I would be able to justify buying a commercial large Dob. Now, grinding mirrors is not for everybody, and that's for a few reasons. I don't actually like doing it. I teach people to do it. I have a mirror grinding machine in my garage. I personally hate grinding mirrors. It's boring and tedious and very loud. The process essentially involves taking a piece of glass like this and grinding it against another piece of hard material. People used to use another piece of glass, but that's pricey. So now we use ceramic tiles, or just somebody had a giant thing of Bondo or something like that, and glued to a piece of plaster. And you just go back and forth for hours and hours, pushing this heavy piece of glass over the tool with abrasives and water in between. And that'll eventually start digging a spherical curve. Now, once you've dug the curve out to the depth you want, you then measure the depth of it, and it'll just naturally be pretty even because some interesting laws of physics and regular surfaces. And from there, you smooth it with finer and finer grits. Then you pour this tar-like stuff called pitch to polish it. And then the real magic is the final stages of polishing, where you have to make what's called basically a very primitive interferometer, and you measure the light coming off of the mirror with either a razor blade or a printed grating. It's called the Foucault or Ronchi test, and you look at the shadow of light cast on the mirror across this razor thin edge, and you can then determine how close the curvature of the mirror is to where you want, and if there are any surface defects in the polish. This is extremely tedious, and 99% of the cost and actual labor of especially larger telescope mirrors that get expensive is that step, because you might have to polish for only 5 minutes, but then you might need to spend 30 minutes waiting for the mirror to cool down from the heat of you rubbing the polishing tool against it, and then tediously examining it to make sure that what you just did to it was an improvement, and if it isn't, how you can go back and fix it. This is not intuitive. It's essentially an art. I would not call it a science. There is no magic way to just produce a parabolic primary mirror with any one technique. It's quite the read to learn up on how to do it, and I'm still not that good at it. But it's extremely rewarding because, again, you are making a surface more than 1/1000th the thickness of a saran wrap flat. Well, not flat, but smooth. And that's pretty impressive for something that you can do, again, on your kitchen table. The photo up top you can see was a mirror making class I did, and I just made these little stands and weighed them down with some weights and concrete blocks, and we ground a couple of mirrors, and it's really not hard. But again, the real thing is it just is tedious doing these repetitive things. Now, many people make a machine, but you can make a machine that spins the mirror and tool around, but you can't make the machine magically clean everything off and feed more grit onto it. So you still have to stand over it doing that. And then in the polishing stage, it's very hard to make a machine that can do these sorts of different hand movements in different directions to make these slight polishing adjustments. And even if you have one of those, you have to know what you're doing with that. I have one of those and I don't know what I'm doing with that. And so it's really not something that you can just walk away from. You really have to be active even if you have a machine. If you can make telescope mirrors, it is like a superpower because you will understand so much about optics and physics that you will bore all of your non-astronomy friends to death, and probably your astronomy friends too. That being said, it's pretty cool, and I'm really glad that I learned how to do it. My roommate's making this 16-inch mirror, and this will have 4 times the light gathering and twice the resolving power of the 8-inch behind me. A 16-inch mirror like this is a pretty hefty piece of glass, but it's considered really the optimal size by many people for viewing things like galaxies and so forth. And a 16-inch telescope made out of one of these mirrors can be pretty compact. You might be able to fit one into a small sports car even if you design it well. Commercial 16-inchers are usually not that compact and will take up a whole car. But again, that's why building one is pretty cool. Now, it used to be, back in the old days, that you sent your mirror off to be vacuum plated with aluminum to get it coated. And when you buy a new telescope, that's what it comes with. Unfortunately, there are only 2 coaters in the United States now willing to do this for amateurs for anything approaching a reasonable price. And both of them could stop at any time. I actually am acquiring a coating machine, so I can offer it as a service to people. But one thing that's really interesting is a really fun bit of science and chemistry that I've gotten to do and that you can do to save some money on making a bigger telescope is spray silvering. You mix silver nitrate and a reducer into a beaker, and you can spray it out of garden pesticide sprayers, actually, that you can get at Home Depot to mix them. And as the silver and reducer hit each other on the mirror, they magically deposit this molecules-thick silver coating. And the silver will tarnish in a few months, and then you'll need to redo it again. But it's so laughably inexpensive to do each time that it would take you decades to cost enough money to equal that of aluminizing a mirror. And that's ignoring the fact that you have to ship the mirrors to get them coated, which can be really scary when you're dealing with a piece of glass that's 20, 30, 40 pounds. I'm sure all of us here are familiar with getting something smashed from FedEx or UPS. And of course, you have to send it twice because it's got to come back too. That was actually what got me into spray silvering. And when I first started doing it, there were still a lot of coaters that were out there, including one in New Jersey, to aluminize mirrors. But I was terrified of shipping it or driving it anywhere, so I decided to silver it in my backyard. Since then, people have developed some ways to protect it from tarnish and so forth. It's really interesting, but it isn't a solution for smaller telescopes. It's kind of a pain to set everything up to silver a little mirror, and the cost of the chemicals is not worth it with a smaller telescope. But it is very interesting, and I just thought I'd talk about it since it's a pretty seldom covered topic. And you might wonder also what makes Dobsonians so great in their simplicity, and that's using them to show other people the night sky. And that's usually what I do. The telescopes behind me, I both regularly set them up downtown here in Tucson to show people the moon and planets, and I'm probably going to do that tonight. And the great thing about Dobsonians is they're dumb and they're simple. If somebody bumps your Dobsonian and shifts it off of your target, all you need to do is just point it back. If you have a computerized telescope and somebody bumps the mount, the likelihood that they didn't jostle the tripod enough to also ruin the alignment of the computer system is near 0. And in addition, there could be, if it's grabbed or suddenly and yanked, which I've seen people do, it could actually damage something. There's also the time and effort to set up. If you're just showing people the moon and planets, why would you spend 20, 30, 40 minutes setting up a big telescope on a tripod that's got all these, these pieces and all that, when a small Dobsonian or a big one is gonna provide just as good of a view, and you can just simply pick it up and walk away when you're done. That's really the best part. Dobsonians are easy to just bolt wheels onto with the larger ones as well for transporting them around, and the truss tubes can be broken down to fit in a pretty small space. And again, Hadley back there is great because you can just pick it up with one hand. And that's really why I build these telescopes and continue to innovate with them. It's because the more capable and portable telescopes can be, the more opportunities there are to give people the best possible views of the night sky and in anywhere they might be. Now, I hope this has been informative and interesting presentation. This is my first one in a while, and it's my first one quite like this in this format. So thank you, and I hope that I've provided some useful information.
I do have to say, I was pretty jealous when you showed the picture of was it the 24-inch?
Yeah, I sold that. I miss it. I'm hoping to make another scope around that size, but this time I'm gonna grind the mirror.
Yeah, I only have a 10-inch only,
Oh
but
yeah, I
there's
have
always,
I have the
aperture jealousy, right?
yeah, I have the Explore Scientific 10-inch that they sell at Costco, which is a really weird and cool scope. And I also have a C11. My roommate has a 4-inch refractor, and I have my 14-inch, which I'm currently have disassembled in a pile of parts because I'm redesigning it for the literal 30th time.
Any questions? Yes.
How long does it take you to build like a full telescope, like on average?
So if you're, with like an 8 or 10 or 12, the normal reasonable size to start with, if you're just building the scope and you're just doing a Dobsonian like this with just a solid tube, no trusses, nothing complicated like that, you can throw that together, just the structure itself in a day. It really depends, like if you want to finish the wood nicely or put paint on it, or if you want to like smooth out the tube or anything like that. That's honestly more time consuming than actually building anything. If you're building a truss tube Dob, the structure really that just depends on how you do it. Like I like to just kind of fool around with parts in the shop and make things work, and that's probably dumb and way slower than just designing something in CAD. The people I've seen who design stuff in CAD can crank out a truss tube scope that's pretty large in a few days. The 24 I did, that big blue one, was pretty simple, and I built the whole structure for that in maybe 4 or 5 days of just working on it for a few hours in the afternoon. If you're grinding the mirrors, that's really a different story because it depends on a lot of things between, well, first off, you're using any kind of machine or just a turntable to spin it, how big your mirror is, how thick the mirror is, the kind of tool you're using. But if you're grinding a 16-inch like this, my roommate so he's dug out the curve in this. I don't know, well, you can see it's f3.7, which is a pretty deep curve. It's about a third of an inch deep. He's removed about 2 pounds of glass. Now, you can also buy glass sometimes that has a curve already in it or something, but in any case, digging out the curve in a small mirror might be 12 hours, a big mirror like this, 20. Then actually doing the grinding and grinding itself is maybe 10 to 20 hours with pretty much any size mirror. And then polishing, really, there's a lot of things that go into that, but that can be somewhere between 10, 20, 30, 40 hours. And then the final part is just, after you've polished it out, you have to make the curve smooth and parabolic and what you want. And that's really as much time as you want. But that I've seen, I've seen people parabolize some pretty difficult large mirrors with some pretty steep curves in a couple of hours. So I would say if you're building just the structure for a bigger scope, it's like a week. If you're doing just, a simple Dobsonian, it's a weekend. If you're doing a small mirror, it's a month project. If you kind of, put like an hour into it here or there. If you're doing a big mirror, you're going to be working at it for a while. They're big commitments. But it really depends on what you want out of it and how big of a telescope you're doing. And you can also cut a lot of corners or take shortcuts. If you don't want to build your own support for the mirror, you can buy one that's pre-made. If you don't want to deal with grinding a mirror, you can buy a mirror pretty easily. It's just at the larger sizes there are less options, and you might not be able to always guarantee the quality. And things like the design of the base, really optimizing the weight of it. A lot of people change aspects of the design, but it really is just about how much effort you want to put in. You can throw together one in a weekend. Hadley, you can literally put together in an hour after it's printed.
Yeah. This is all fine and good. Well, you sort of mentioned that you and I, this is one of the reasons why I'd never make a telescope myself is because I don't want to grind the mirror. I don't want to spend that
Yeah, that's understandable.
and tedious amount of effort to grind the mirror. So that's one thing. The other thing, reason for spending thousands of dollars and getting a pre-manufactured telescope is because, and one that's computerized is, again, again, when you're making a Dob like this, very simple, you have no mechanism for keeping the, a clock mechanism.
Oh, you could make an equatorial platform very easily. And those are not expensive. Also, there's do-it-yourself go-to systems like OnStep that are not terribly expensive. You can computerize even a large Dob for a couple $100. It's just whether or not you want to do that. And of course, it does require some effort and work. If you really just want a simple computerized telescope, the questions I would have are, why are you dealing with computers for a telescope that is small enough that all of the things you can see with it are easily found? Why not just get something with tracking? And if you're dealing with a bigger computerized one, well, why, are you willing to deal with setting that up? Because that's quite a lot of effort. And of course, again, bottom line, you don't necessarily need tracking, and adding tracking to a Dobsonian is not some sort of impossible thing. It's actually quite easy.
Have you ever heard of an outfit called Romer Optics?
Yes, I have.
I have a 10-inch Dobsonian, and I, for $99, attached 2 equatorial devices on it that allow
Platforms.
you,
Yeah, I've heard of this guy.
right, and then you just push, it connects with your cell phone as an app through Wi-Fi, and you just select the item you want to look at, and then push it.
Yeah, the push to. Yes, that's right. The Romer Optics Easy Push to. So yeah, that'll just tell you how to find things. It doesn't track, but push to systems like that, there are a million. So some are like that. The Romer Optics.
He does offer a tracking kit. You can.
Oh, he has a go-to kit now. That's awesome. Yeah. So that's what I mentioned. That's like OnStep. It's it's a computerized system. And then there are just the push to encoder systems or and stuff like that, where you either have a hardware thing that tells that has a little wheel in it that tells a computer chip how far your telescope has rotated around, and then tells you where you are in the sky. Or there's systems now that use a small camera or even your phone camera, like the Pi Finder or the StarSense Explorer, show you where you are. And that's really cool. There's also Astro Hopper. That's another one. Doesn't work as well.
Yeah, because I don't have that much interest in the tracking and astrophotography. There's too much time involved. You talk about time for mirrors, but time for layering stuff, and I'm not that computer versed. That I just enjoy finding the objects.
Yeah.
System makes it so easy.
Yeah, and the push to systems like that have gotten so affordable. I mean, that now they're pretty trivial to add on. I remember when I was building scopes, they were a real commitment. You had to buy a Sky Commander and spend like $500 to $1,000. Now it's like $100 for just encoders and stuff.
When you talk about computerizing a telescope, do you have to make it, or can you use one that's pre-bought and then computerize it on your own?
So the Romer Optics kit and stuff like that, you can add go-to on or push to onto an existing telescope that you've made yourself or a commercial one. I would say if you're buying a commercial scope, I wouldn't buy a commercial scope and then add a go-to kit to it, because there are commercial Dobs that have go-to, and that's usually a more user-friendly system than the add-on kits. But either way, you can do it. You can do it either way. You can, and also you can completely do it yourself with like an Arduino and some basic hardware, and you can make a push to system for like $20 if you really want to be cheap. Go-to with motors is really the hard part, because you do need powerful motors to move a bigger telescope, and those can get pricey. And you need to have accuracy, which gets pricey.
Have you been to Brunswick telescope?
I don't think you heard the question.
I couldn't hear that, no.
Have you seen Mars with your telescope?
Yeah, it's been a while. Mars right now rises like an hour, I think, before the sun does. And I think the last time I've even seen it at all must have been a year ago now. But yeah, I have. Mars is going to be back at the end of this year. It's going to be getting closer to Earth again. Mars doesn't have a perfectly circular orbit though, and it's right now when it gets close to Earth, it's going to be about as far from the sun as it gets, and it's like half again as far from Earth as when it gets to the closest approaches. So it won't look as big or bright as it did a few years ago in the past few oppositions. This is, I think, it's the next one is the worst one. But when Mars is close to Earth during opposition, you can see with Hadley there, you can see the polar ice cap and some dark markings. But with a bigger telescope, it mostly comes down to how steady the atmosphere is. But with an 8-inch telescope like this one, you can see a bunch of dark markings on Mars, and sometimes you can barely see a few of the volcanoes and Valles Marineris, but the giant canyon. But the dark markings you see, they're just patches of dark sand, and astronomers actually used to think they were living things because they change in size and shape slightly, but it's just blowing dust.
Where do you find suppliers?
Pardon?
On it, suppliers?
Where do you find your
For
supplies?
parts
Yeah,
and
where's
stuff.
he buy his supplies?
So with anything other than the optics, it's all just, it's anything standard hardware store, we're working with normal screws and plywood here. With things like eyepieces and stuff, there's dedicated astronomy retailers, and they'll also sell you a focuser or finder. For the optics, really, the best place to shop for used optics is an astronomy site like Cloudy Nights, or an astronomy group on Facebook, or through a local club that knows a place to get them. If you want to grind your own mirror, obtaining glass has become an absolute nightmare, but there's a site called First Hand Discovery that still offers glass blanks and kits. And what I've been trying to do is obtain, if you go on eBay and try to find just the glass for a 16-inch porthole like this one, you can find a glass for a 16-inch for only like $100. The only thing is you just have to make sure it's not tempered. And the way you do that, actually, you can examine it with polarized light, but if you're looking at an eBay listing, you look for chips. Tempered glass doesn't chip, it breaks. You can't grind tempered glass into a mirror. But if you have a piece of glass that's got chips like this, it's at least usable for a telescope mirror because it's not tempered. It's definitely annealed in some way. But yeah, and this is from the USS Oriskany. If you've actually ever watched Top Gun, this piece of glass was technically in it for like 2 seconds.
Oh, wow. What a great.
That's a nice fun fact.
Yeah. But it is harder now to find suppliers for a lot of these things. It can be a little confusing, and really the best way is to try to go through your local, your local astronomy group, or through sites like Cloudy Nights, and find people who can direct you, because well, even if I could come up with a lot of suppliers for some of this stuff right now, anything I say could be incorrect in a few weeks or months because people are closing down these things all the time. I'm actually obtaining a vacuum chamber to illuminize mirrors so I can offer people reasonably priced mirror coatings so they don't have to silver or pay for a research lab to coat their mirror for way more than the glass itself costs. Yeah, it's actually the one, if you look up, there's a really great documentary by John Dobson that I highly recommend that's on YouTube. It's just called Telescope Making with John Dobson. And he turns a 16-inch porthole like that one into a mirror and telescope over the course of about 90 minutes. And he goes over the grinding and polishing process very simply. And at the end, he gets it illuminized. And the illuminizing machine that is used in that video is actually the one I'm getting.
Really?
Yeah.
I have a lot of friends, when we get a new telescope, we pick out a particular deep sky object for first light. Do you do that with each of your new telescopes?
Oh, yeah.
Second part is, what is your favorite deep sky object?
So for first light, I like to do, well, it depends on how complete the scope is when I'm testing it too, because if it's not, the mirror's not coated or anything, it's easier to do the moon or a planet. But if it's got a coated mirror, or I'm already at that, and I'm at that point, I like to do the double cluster, because it's always just it's probably one of the things I look at most in the sky, because it's up for most of the year and it's bright and it's easy to find. And, you have a bunch of these moderately dim stars with all these vivid colors, and it's a good way to just kind of gauge at a glance how well your telescope performs. And also it's just a really nice object in almost any instrument, even binoculars. It looks pretty cool. My favorite deep sky object, though, is a really hard question, but I would have to say probably like the Lagoon Nebula and or the Veil. It's a really hard choice between the two because I like them for completely different reasons.
Yeah, the Veil is, here in New Jersey, it's impossible, but when I do go up to Pennsylvania, it's really cool just to find it.
Yeah. You can see it from a pretty light polluted place. It really just comes down to getting a good nebula filter. And unfortunately, a lot of the so-called O3 and UHC nebula filters that get sold are just they're not actually up to spec at all. Or they're literally like, there's an oxygen 3 filter that's sold on Amazon by those SV Bony guys, and it's actually a UHC filter. But if you have a good filter, you can see the Veil from a pretty light polluted place and with a small telescope. It's just about a good filter. Veil's weird like that.
I was wondering, do you have the steps to create a telescope like documented from beginning to end?
No, but the Stellafane, so there's the Stellafane website, stellafane.org. And I have some links on my social media to stuff as well. And again, the John Dobson documentary that's on YouTube is a really good starting point. And if you're familiar with things like Reddit or Discord, there's the Observational Astronomy Discord and Reddit/r/telescopes, and those also have tons of resources on astronomy and telescopes in general and telescope making. And of course, there's my site, telescopicwatch.com, and we are working on, I'm going to have some stuff on how to build a scope and fixing them and so forth. I'm working on a lot of videos for that as well.
Great. Well, it looks like we have no more questions. Last call. Okay. Zane, thank you so much for reaching out. I'm so glad you were able to come join us virtually and go into building a Dobsonian telescope. Thank you so much. And we'll be sure to share the recording of the
Yes. And by the way, again with Hadley, you can just look up Hadley Telescope, and there's a site on it's on printables.com, and there's a whole thing explaining it by then going into everything you need to do to make one, and there's how and whatnot. And you can also buy pre-printed stuff from the guy who designed it if you don't have a 3D printer. He sells whole kits too.
Well, thank you again. I'm really happy you reached out and we were able to arrange this.
Thank you so much.
Take care.
Thank you.
Bye.